everyone, and especially warm welcome to our host, the Modern Agriculture Foundation, Neta and Ronnie. My name is Gabriela Meyer and I am the owner of Bioengineering, a family-owned company in the Swiss Alps. Before I pass the stage to Gero, our engineer, who will take you to a deep, detailed, professional journey, I would like to travel with you to a tour into the farmer world 50 years ago. The company my father founded as a pioneer like you, 72, had the vision to give this growing industry the best equipment. If you look now what pharma industry achieved, you probably can imagine what happened. We in Bioengineering are welcoming you to share, learn, consult. It is an honor for us to pass our experience and share our knowledge with you. Our past experience enable us today to accompany you, the treasurers, the pioneers of those important startups, to influence together our needs, the needs of our planet, our common source. We are engaged together with the Swiss major players that are with us today, enable these startups to perform versus regulation, scalability, cost reduction, to allow humanity of today to explore the protein revolution, a sustainable living. Bioengineering has sustainable solution for bioreactors and fermenters from a lab scale up to a large production plant. Being a family-owned company allows us the flexibility of building up system tailor-made for your needs, from the idea to reality. Wishing you all good luck and prosperous cooperation. Bye!
Okay, so our next speaker is Gero Greive. I hope I say the name correctly. Sorry, I'm not used to Swiss names. So Gero is the head of process engineering at Bioengineering, a Swiss company that has designed and fabricated benchtop scale research bioreactors to commercial production plants in Israel and around the world for biopharmaceutical, food, and fine chemicals applications. Prior to that, Gero has worked as project manager and process engineer for the upscaling, engineering, and execution of turnkey projects that include some of the largest operational mammalian cell culture bioreactors today, with capacities upwards of 20,000 liters. In addition, he has led Bioengineering's R&D team for continuous growth systems, HTST, dilution and perfusion, and process simulation, liquid and gas CFD, sorry. Gero has a keen interest in cell-based alternative protein and is working with cell-based meat, fish, and fat companies to address upscaling challenges and usher in the next agriculture revolution. Let's go. Gero, can you hear us?
Yeah, I can hear you. Give me a second.
Good luck.
Yeah, thank you. Can you see me? And hopefully my presentation. And my presentation, oh, can you see that? Hello? Hello? Is my screen sharing?
Gero, can you hear me?
Yeah, I can hear you.
We hear and see you perfectly. You can start.
Ah, okay, okay. So you saw also the presentation, right? This doesn't work. But can you see my presentation? That's the question. Okay, so then I go on with the presentation. Yeah, so thank you. I'm very pleased to be here, and I would like to say hello.
Gero, can you hear me?
Yes.
Please press the present button so we can see it in the full screen mode.
Like this?
No, not yet.
Not yet.
We still see you not in the correct mode. The PowerPoint version you have is in German, so I cannot support you. Sorry.
Okay.
Now we see the full screen. Now we see the presentation.
So you see the full screen.
So we can do it like this, Gero.
Okay. So yeah, again, thank you to invite me here to this event, and yeah, hello from Switzerland. My name is Gero, and I'm the head of process engineering at Bioengineering. I started my way as a process developer for the chemical industry, and I was specialized on upscaling for bulk production. So actually here at Bioengineering, we established an upscaling concept from the bench to the commercial scale, which we already used several times in the pharma. And I would like to support now your business to the next revolution. And of course, the questions which come always up is how can I upscale my process, and how can I commercialize my cultivation for meat, for fish, for fat, etc. So when we look at this GFI landscape, there are a lot of challenges waiting for us. And we would like to bring in our experience in the design of fermentation tanks and the cell culture media, scaffold handlings, bioreactor design, but also we have experience with the facility design. And of course, because we are normally in the pharma industry, we have a lot of knowledge about safety regulatories, QA, etc. From the process perspective, we have four challenges. The cells are grown in suspension or arterial. We need to appropriate aeration. The agitation and the shear forces is every time a problem. And the recycling of the cell culture media is one thing which can help you to reduce your production costs. So when we go ahead, planning now for what comes next is definitely the selection of the right pilot bioreactor. Most of you are in the lab or in the bench phase, I think, and you are dreaming of a biofarm or a 100,000 liter bioreactor, etc. And in such a big scale, there are a lot of problems. For example, reducing the mixing efficiency, reduced KLA. In a big vessel, there are some gradients, temperature gradients, oxygen gradients, pH, and of course, substrate gradients. And to solve all these problems, mixing is the first choice to the process more efficient. But with mixing, there comes up the shear forces and the shear stress points. In general, the shear stresses are generated by mechanical forces, which are inducted by the friction of the liquid on the cell surface. And these shear forces have negative influence on the viability of the cells and, yes, as well as the yield. These shear forces are generated by two types. One of them is the type and the number of the impellers, as you see here on the right side, and the slip velocity of the aeration. This is not common known, but the velocity of such a bubble generates also shear forces. Yeah, I would like to quickly go to shear stress by agitation. To find the right agitation strategy is very important. For example, we have here a correlation between the oxygen transfer, these are here in the diagram, the aeration, and of course agitation and vessel internals. When you have a look at, you will see that with a lower motor speed, lower RPMs, and with a lower aeration rate, you can generate higher KLA values than with a high RPM speed and a high aeration rate. So this is not what you normally do on a bench top. When you need more oxygen in your system, you will rise up your aeration and your speed, right? So this is not scalable for 200 cubic meters and more. We have to focus on the reduction of the power input, because this means that we can reduce shear forces, and of course you can reduce your power consumption, so production costs. Also necessary is to find the right impeller. The homogeneous flow pattern you see on the right side is better for the cells. I think as a seller would like to live in the right side bioreactor, not on the left side bioreactor. But the left side bioreactor is still common practice. With the right side design, you can keep your microcarriers or your cells in suspension. You can increase your dwell time of your gas bubbles. You can increase the mixing performance, and all of this helps you to improve your yield and shorten the batch duration. The other thing was the shear stress by aeration. The sparging is still a robust and well-known method for oxygenation, that's for sure. But the cells can adhere on the bubble surface. They rise up together with the bubbles. This brings the slip velocity and, of course, the shear forces. And when the bubble reaches the surface, there's a high energy dissipation rate when the bubble will burst, and this will carry your cells. So there's an alternative for that. It's a bubble-free aeration. It's well known in the lab scale. But if you imagine this is a silicon hose here, which is on a cage, and when you do this job several times on a 1,000 or 100,000 liter bioreactor to spin this hose around this cage, yeah, you will get crazy. So this is not a good upscaling option for bigger volumes, but for the lab scale, it's okay. For bigger volumes, you need such a stainless steel construction, which the self-supporting aeration modules, that's a silicon glass fiber combination. This construction can be rotated and used as an agitator for a gentle and efficient mixing inside your bioreactor. This construction can be washed down, CIP, SIP, not a problem. You can use this several times before you have to change these models. And yeah, of course, this is one of the ways you can use to aerate your cells bubble-free and reduce your shear forces in the system. So I would like to summarize this technical part of the presentation. When you go back, maybe you can check your system if it is possible to reach a geometrical similarity in your benchtop reactor, for example. It means it's a stirrer scalable is the ratio between the vessel wall and the stirrer scalable. Is it a single-use system, a wave, for example, which is not possible to scale up to 100 or 200,000 liters? You have to think about the agitation and the gassing parameters. As I mentioned before, it's critical to realize 1,200 RPMs in a 200,000 liter bioreactor. That's more or less not possible. I typically recommend a 200-liter bioreactor for a good upscaling process with a multifunctional design for your process intensifications. With such a volume, we can generate a lot of parameters, which helps us to quickly scale up your process to 2,000 or 10,000 liters. The process intensification is definitely one of the things we have to look at. We will do a very fast upscaling because the timeline, the lead time is very short, which you're looking for. For example, I made this slide to show you what is possible when you come from your cell foundings, etc., or from your process intensification with the 200-liter bioreactor. You're very close to a market test train, which is around 2,000 or 5,000 liters. And up to this point, you can optimize your process. That's not a big issue. We can design the process in a multifunctional equipment in a multifunctional way. So you can add perfusion systems, add some other probes, do some inline measurements, etc. But when you shift to the next thing, to the regional and commercial scales, you have to define your process finally. It's necessary to know all the parameters for upscaling, for agitation, for aeration, pumpings, etc. And the other thing, I already talked about this 100 or 200,000 liter bioreactor. This is a technology shift. We already done cell cultivation in a 20,000 liter bioreactor. That's possible now and becomes more and more. But to cultivate the cell in a 200,000 liter bioreactor is still complicated, and we need to think about new concepts, how we can realize that. I would like to explain some points we discussed in a case study, actually. We finished our design of the market test train. And as I mentioned before, we design it in a multifunctional and flexible way. It is very interesting. In this train, you can use the upstream vessels and also as the downstream vessels, just by changing the agitation system. We defined the different scales for the different steps, and we are looking for reusability of this train for inoculation of the commercial scale plant. So our next steps will be actually the N-3 is a rocker, a wave back, and we would like to implement a continuous system and delete this rocker system. A continuous system to inoculate several seed reactors, because our goal is to generate a more or less continuous production. And we are also looking forward to reduce the N-1 step, because this can help us to reduce the production time. Yeah, we're still working on all these ideas with our customer, as I mentioned before, in this 200-liter bioreactor to get the necessary process parameters. So planning ahead, our next steps for the customer, he's still working on it, is a process optimization. You try carrier scaffolds, but you also would like to do it with cells which are just in suspension. As my colleagues from Bühler already explained, the bioprinting is a point you have to look at. The market testing, how is the acceptance of the customers, and also the regulatory approvals are an open thing. Next steps for us are actually the design of the supply, the regional supply reactor, the 20K liter bioreactor. we have a small team which is working on the technology shift for this multifunctional worldwide commercial scale plants. And we have to define the relation between the scale up, means in volume, and the scale out, means in area. So this is a discussion about the biofarms or the big facilities which we know from insulin production or other yeast productions. The continuing of the process optimization together with the customer is very time intensive, and of course the cost optimization and the regulatory affairs are in our point of interest. So I quickly achieve some commercial scale for you to capture the market now. These are 5 points I would like to give you to think about. The novel designs which are in the room are great, but they required a lot of time for the proof of concept. And time is, it's a very quick market, you know it better than me. The multi-purpose design is always possible, but I strictly recommend to get in touch with the equipment supplier very early to explain your problems, your ideas, and also the reusability and flexibility of such a plan must be provided to your equipment supplier very early, because then we know how we can design, how we can help you to design such a flexible plant for your research and scale up things. And when the test market plant is reached and you have a test market train, then I think the bottleneck will be the founding, because the equipment lead time is more or less a maximum of 1 year, for example. But the founding rounds are always a bit, need so much more time. You can order directly now a 20,000 liter bioreactor here, and you will get this within 1 year in place. But the question is, how was your founding? How was your money saving things? So please decide on your cost-cutting approach very early. Go in touch with equipment supplier very early. For example, when you come in contact with us, of course we have flexible benchtop equipment here. As you can see here on the slides, we can implement, for example, an airlift or a fixed bed or a continuous production system. And when we work together just from the beginning, we can bring in our experience, you can bring your experience, and we can work together to design the first a bigger vessel, let's say this 200 liter bioreactor, and to do with these parameters, we can definitely save a lot of time in this upscaling issue for the cultivated meat production. Yeah, so I will come to the end now, and I'm open for your questions and would like to say thank you, and yeah, here we go.
Thank you very much, Gero. Can you hear me?
Yeah, I can hear you.
Thank you for the very interesting presentation. We have two questions from the audience.
Okay.
The first one is, one second. Should food tech companies use the same equipment, material, and quality requirements as required for a pharmaceutical plant, or can they choose something different in order to reduce the enormous costs?
Yeah, so this is exactly what I mean with come earlier to your equipment supplier. Yes, the material which we use in a pharmaceutical plant is very expensive, and also the surface finish is very expensive. But for example, when you use lower quality steel and you put it in your benchtop reactor, and you look at what has happened with the steel when because there's some corrosion, etc., or rust generated by your media, then you will know that you need a higher quality steel. And also for the surface finish, in the pharmaceutical area, this is around 0.6 microns, just because of this cleaning efficiency, right? And the microbarrier, the cross-contaminations, etc. But maybe for your process, it's also applicable to use 0.8 microns as a surface finish, or 1 micron as a surface finish. And this has a very huge impact on your investment cost for this materials.
Understood, thank you. How can an Israeli entrepreneur that is interested in developing a product in a bioreactor address you, find you in this COVID-19 time? How can they work together with you?
Yeah, so we can use this beautiful Zoom things or team meetings. That's what we do several times. Yeah, you can write me an email, and we can choose a date, and we can speak about your process, and I can bring in some information and make some recommendation for you what you can test in your benchtop to generate some upscaling parameters, or give me an idea how can I support you with upscaling, right? This, yeah, that's a good way. Call me or write me an email.
Okay. So thank you for the answers. It was great having you with us, and I hope that next year in our international event here in Israel, you will be with us live and able to talk with the audience yourself. So again, thank you very much, Gero.
You're very welcome.